It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are going to do practice problems of Newton's laws. Oh, hey Al, didn't see you there. How's your cousin wife doing? Good, sweet. The first problem we're going to look at is number 1, an unbalanced force of 45 newtons. That will represent our net force. So F net equals 45 newtons. Is applied to a 5 kilogram mass, initially at rest, which means VI is 0 meters per second. How far will it travel in 3 seconds? We're given the time, and we want to find the distance. Because the object is initially at rest, and then it's going to speed up, that means it's accelerating. And we don't know the acceleration in this problem, so we have to find it first. What we could do is utilize Newton's second law, where A, the acceleration, is the net force over the mass. We know the mass and the net force, so we can just plug and chug, and we get 45 newtons all over 5 kilograms, gives us 9 meters per second squared for the acceleration. Now that we know the acceleration, we know the initial velocity, the time, we can find the distance. The formula we can use for that is d equals VIT plus 1/2 AT squared. VIT goes away because the initial velocity is 0. That leaves us with d equals 1/2, 9 meters per second squared, times 3 seconds squared. 9 times 9 is 81. Half of 81 is 40.5 meters. And that gives us the distance. Letter A asks, what is the final velocity after 3 seconds? So VF equals question mark. We can use VI, T, A, and D to solve for VF. I'm going to use VF equals VI plus AT. VI is 0, so VF equals VF equals 9 meters per second squared times the time of 3 seconds. That gives us 27 meters per second. Number 2. Number 2, a 1,500 kilogram tractor, M equals 1,500 kilograms, is traveling 35 meters per second east, VI equals 35 meters per second. We'll make it positive for east. The driver spots a tree in the road up ahead 1,000 meters. What braking force must be applied in order to stop the truck in time? That means the final velocity is 0 meters per second. And we want to find, again, the net force from the truck. In this case, in order to find the net force, we need to know both the mass and the acceleration. We know the mass, but not the acceleration. So we have to find the acceleration first using VI, D, and VF. We can use VF squared equals VI squared plus 2AD. Vf is 0 because the truck comes to a stop. We'll subtract vi squared, divide by 2d. That leaves us with a equals negative vi squared over 2d. If we plug in chug, negative goes on the outside. 35 meters per second quantity squared, all over 2 times 1,000 meters. We plug in our calculators and we get an acceleration of negative 0.61 meters per second squared. That negative represents the fact that the tractor trailer is stopping, which means it's slowing down, so therefore it's going to have a negative acceleration. Now we can find the net force using Newton's second law. A equals F net over m. Multiply both sides by the mass. F net is ma. Plug and chug. F net is 1,500 kilograms times a, which is negative 0.61 meters per second squared. Let me move my face out of the way. Sorry about that. And we get F net to equal negative 915 newtons. That negative force represents the force being applied is in the opposite direction of motion, so it's directed in the west direction. Number 3, Brittany is pulling Bella around in a box, for whatever reason. Bella and the box have a combined mass of 100 kilograms. The coefficient of friction is 0.05. If Brittany applies a force of 250 newtons relative to the handle that makes an angle of 30 degrees with the ground, what is the acceleration of the box? Because we have multiple forces acting on Bella in the box, let's draw a vector diagram. This dot will represent Bella and the box. We know that downwards is the force of gravity, and upwards, the upwards force is a normal force. That's the table pushing up on Bella and the box. We're told that there's a coefficient of friction, which means there's a force of friction going in the opposite direction, F of F, and that Brittany is applying a force at an angle of 250 newtons. We'll call that F sub B, 250 newtons. That creates an angle relative to the ground, so we'll draw another vector going to the right. That'll represent our F of X vector. That's the force of Brittany in the X direction. And we also have the force of Brittany in the Y direction, let's call F of Y. And then also theta, which is 30 degrees. And our goal is to solve for the acceleration of Bella and the box. As we could see, Bella is accelerating in the horizontal plane, so we want to solve for the acceleration in the x direction. But let's analyze this in the vertical direction first, using Newton's second law. We have A equals, let me use purple to be consistent, sorry. In the y direction, Newton's second law, A equals the net force all over the mass. We have to look at all the forces in the y direction. We have 3 of them. There's F of n going upwards, F of y going upwards, and F of g going down. So we'll make F of g negative. That leaves us with A equals F sub n plus F sub y minus F sub g all over the mass. Let's multiply the mass onto the other side. MA equals Fn plus Fy minus F of g. Bella and the box are not accelerating in the vertical direction. She's only moving horizontally. So we can get rid of m times a. We can calculate F sub y because we know the hypotenuse and the angle. We can calculate F of g because we know the mass of Bella in the box and the acceleration due to gravity on Earth. What we don't know is the normal force. So let's isolate that. F of n equals, we'll add f of g to the other side and subtract f of y. The formula for the force due to gravity is the mass times the acceleration due to gravity minus the force in the y direction is FB sine of theta. So it's the hypotenuse times the sine of the angle between the ground and the handle. So that'll leave us with F of Bella times the sine of theta. Let's leave this at that. We could plug and chug the values in, but we'll do that at the end. And let's look at the forces in the x direction. We'll start off with the same thing. A equals F net over m. This time we're just going to look at the forces in the x direction. F of Brittany, in the x direction is to the right, minus the force of friction to the left, all over the mass of Bella and the box. We're solving for the acceleration, so it's not going to be 0, or it probably won't be 0. So let's break down the formulas. F of x, that's the force of Brittany in the x direction. It's adjacent to the angle, so it'll be the force of Brittany times the cosine of theta, minus mu, the formula for force of friction, minus F of F, the formula for force of friction is mu F of n, all over the mass. We know the force of Bella, we know theta, we know mu. The normal force we solve for in the vertical direction, it's mg minus fb sine of theta, so let's plug that in. A equals fb cosine of theta minus mu times all of fn. mg minus fb sine of theta all over the mass. In this case, nothing cancels out, so all we have to do is just plug and chug. Sorry for running out of space. Hopefully you're writing smarter than I am. So we get A equals 250 newtons times the cosine of 30 degrees minus mu 0.05. Let's make a bracket, and then we have mg, so that's 100 kilograms, times g, 9.81 meters per second squared, minus the force of Bella again, 250 newtons, times the sine of 30 degrees. And this entire thing is all over the mass of 100 kilograms. Plug this in our calculator, make sure we're in degrees, and we take into account brackets and parentheses, and we get an acceleration of 1.74 meters per second squared. Let's look at number 4. The leg and cast in the figure below weigh 220 newtons. That's W1. Determine the weight, W2, and the angle alpha so that no force is exerted on the hip joint by the leg plus the cast. We've got multiple forces in this picture, so let's simplify it, get rid of my amazing drawing, and just look at the component forces and make a vector diagram. We'll make the dot where the person's leg is. Let's start with F of G going downwards. And then we're going to add in our resultant forces. We'll look at the one going to the right. Let's just call that F of 2. That's the force and the tension going up and to the right. And we also have F of 1 going up and to the left. We could break this down into its components. So let's look at the right components first. Let's say f(1) of x, f(2) of x is going to the right. f(1)x is going to the left. And then we also have more vertical forces. Those are upwards. Again, that's a tension of the rope pulling upwards, or string. f(2y) going up, and that's what we want to find, and f(1y) going up. Okay, and let's label what we know. F(1) we're told is 110 newtons. That's the tension in the rope. We're also told the angle on the left side is 40 degrees. We know F of G is 220 newtons. What we want to find are both alpha and F of 2. Because the person is, or the situation is not accelerating, let's set this up like we did for the previous problem, where we analyze this both vertically and horizontally. The order doesn't matter, but we'll be consistent and start with the vertical aspect first. Same thing, begin with Newton's second law, A equals F net over M. And we're looking at just the vertical forces. We have F1I going up, F2Y going up, FG going down. Breaking down F net, that leaves us with F1Y plus F2Y minus F of G all over the mass. Same as the previous problem, multiply both sides by M. MA gives us F1Y plus F2Y minus F of G. The person is not accelerating vertically. Their leg is motionless, so MA goes away. F1Y we can calculate because we know F1 and theta. F of G we're given, it's 220 newtons. So let's solve for F2Y. So we'll add FG to the other side and add F1Y to the other side. F2Y equals F of G minus F1Y. Let's break down F2Y and F1Y based on their components. So F2Y will be F2, it's opposite the angle, so sine of alpha, equals F of G. We could keep it as that because we know it's F of G is 220 newtons, minus F1Y. We know F1, we know theta, so minus F1 sine of theta. And we want to ultimately solve for F2 and alpha. So now we have one equation but two unknowns, which means we need to make a second equation so we can get two equations, two unknowns. Let's look at the x direction. In second law, A equals F net over M. In the x direction, we have F2x to the right, F1x to the left. A equals F2 of x minus F1x all over the mass. Again, multiply both sides by the mass, so MA equals F2x minus F1x. MA goes away because the person is not accelerating. Let's just keep it simple and add F1x to the other side. F1x equals F2x. Sorry, really thirsty. Let's break down both of these. F1x is adjacent to the angle, so that turns into F1 cosine of theta equals F2x is also adjacent to the angle, F2 cosine of alpha. Okay, now we have our two equations and our two unknowns. And our job next, or next job, sorry, is to figure out how to solve for one of the variables. Sorry, getting tangled up. If you learned this in math class, we have multiple options. One option is we could solve for f of 2, get it by itself, and then plug in whatever it's equal to into the other equation. That's option 1, so solve by substitution. Option 2 is solve by elimination. So we can stagger both of these equations on top of each other and either add or subtract to get rid of one of the variables. But there's a third equation that we can do, a third option we could do by solving by elimination, and we could divide both of these by each other. As we could see, we have an f2 sine of theta on the left equation and an f2 cosine of alpha, f2 sine of alpha on the left equation, f2 cosine alpha on the right equation. If we divide these, the f2's will go away. Sine over cosine gives us tangent, so that'll help simplify that as well. I'm going to do the division because it requires the least amount of work. So let's divide the left equation by the right one. So f1, I'm also going to rotate these, which is perfectly fine, so they're all lined up. f2 cosine alpha minus f1 cosine theta. The f2 turns into 1, so we're left with tangent of alpha equals everything on the right side. fg minus f1 sine of theta all over f1 cosine of theta. We know all of the variables on the right side, so we're just going to solve for alpha. Let's take the second tan or inverse tan. That leaves us with tan negative 1 of everything on the right side of the equation. Let's just plug in our variables. 220 newtons minus 110 newtons sine of 40 degrees all over 110 newtons cosine 40 degrees. Plug and chug, make sure we're in degrees, and we'll get an angle of 61 degrees. So alpha equals 61 degrees. That's the first part of the equation, or problem. This is the longest step. Now we want to solve for f of 2. We know, let's look at the smaller equation. f1 cosine theta equals f2 cosine alpha. Now that we know alpha, we could divide both sides by cosine alpha and solve for f of 2. That brings us to f of 2 equals f1 cosine theta all over cosine alpha. Plug and chug, f1 110 newtons, cosine of 40 degrees, all over cosine 61 degrees. That leaves us with f2 to equal 174 newtons. That's the tension force pulling upwards to prevent this person's leg from accelerating or moving. Let's go to number 5. 2 packing crates of masses 10 kilograms and 5 kilograms are connected by a light string that passes over a frictionless pulley as shown below. The 5 kilogram crate lies on a smooth incline of 40 degrees. Smooth tells us that there's no friction on it, so a frictionless incline. Letter A, find the acceleration of the 5 kilogram crate. B, find the tension in the string. As we could see here, both of these masses, the 10 kilogram and the 5 kilogram, are connected to the same string. So we have to take into account Newton's third law that says that the force that the 10 kilogram mass is pulling on the 5 is the same as the force that the 5 pulls on the 10, but they're in opposite directions. When we set up our problem, we have to take into account that the forces are going in opposite directions. What I'm going to do to help simplify things is we're going to say that the direction of the acceleration is in the positive direction. The 10 kilogram mass is accelerating downwards, so we're going to say that down is positive. The 5 kilogram mass is accelerating up and to the left, so we'll say that direction, oops, bad drawing, up and to the left is positive as well. So let's look at, in this case, we want to look at each object individually. We'll look at object 1 and object 2. We're going to look at all the forces acting on those individually. So that's how we're going to separate this. Let's draw a free body diagram for object 1. That's the 10 kilogram mass. F of g is going down, but again, that'll be positive, because down is positive. And then upwards, let's just call that the tension force, so we call it F of t. But again, that's negative because it's in the opposite direction of the acceleration. Looking at object 1, again, we'll start with Newton's second law. A equals F net over the mass. A equals the net force. We know F of g is going down, but that's the positive direction, which makes it F of g is positive minus F of t all over the mass. For this example, we'll multiply both sides by the mass. So we have ma. We don't know the weight or the force of gravity, so we could break that down into mg. Lastly, minus F of t, which is what we're solving for, or the acceleration. We have one equation, two unknowns, which means we need to build our second equation. To do that, let's look at object 2. Object 2 is on an incline, so what we have to do is we're going to rotate our coordinate plane, or xy axis, to make the math easier. Our positive y direction is going to be perpendicular to the inclined plane. And our positive x direction will be parallel to the inclined plane. In this case, it's going to go to the left because we said the left is positive. So all we did was we took our coordinate plane, rotated it to make y perpendicular and x parallel. Once we have that, we now have to draw a free body diagram because there's multiple forces acting on object 2. So to the right, we'll draw our free body diagram. First thing we can always start off with is F of g. That goes straight down. We know F of t that we're given. That's the direction of the acceleration. There's no friction going to the right, or down and to the right, because it's frictionless. And we also have the normal force. And the normal force is perpendicular to the surface. That's going to be along the y-axis, F of n. As you can see, we have an angle, because we're on an inclined plane. The force that we have to split up into its components are the force of gravity, which means we're going to have the force of gravity in the y direction. And again, the y direction is perpendicular to the surface. And we're also going to have the force of gravity in the x direction, parallel to the surface, Fg of x. The angle that we're given, 40 degrees, is also the angle between FGY and FG. So 40 degrees, also in the top right corner. Now that we have this, let's look at the direction that object 2 is accelerating. It's accelerating in the x direction. So let's start off analyzing Newton's second law in the x direction, and hopefully we don't have to do the y direction as well. A equals F net over m. The two forces acting on object F2 in the x direction are the tension force. It's going to the left, but that's our positive direction. And FGX is going to the right, but that's our negative direction. Which leaves us with F of t minus FGX all over the mass. Let's multiply both sides by the mass. MA equals FT minus FGX. We want to solve for the acceleration and the tension force. We can break down FGX, and we can even solve for it because we know the mass of object 2. I should have been more explicit earlier on, sorry. We should label our masses on the left side M1, 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 and on the right side M2. But we have to break down FGX, so let's do that next. M2A equals F2 minus FGX will be, we want to find in terms of FG. Notice FGX is opposite the angle. So even though it's FGX, since it's opposite, we have to use sine of theta. Which means F of GX turns into FG sine of theta. And from before, we know FG is M times G. We're looking at object 2, so it's M2 times G. M2A equals FT minus M2G sine of theta. We have two equations. M1A equals M1G minus FT. M2A equals FT minus M2G sine of theta. And what we want to find are either, both but not at the same time, the acceleration and the tension force. We have three options. We could solve by substitution, elimination, or what we just learned in the previous problem, division. I'm going to choose elimination since we have an FT by itself and an FT by itself. So all we have to do is just add up these two equations together. Notice, so just add up the two equations. I'll rewrite it. M1A equals M1G minus F of t. The other equation, M2A equals F of t minus minus M2G sine theta. Our F of t's, we have a negative on the top and a positive on the bottom, so those become 0. Now we just add up our equations. M1A plus M2A equals M1G minus M2G sine of theta. In this case, we're going to solve for the acceleration first. We have the accelerations on the left side. So let's pull out the acceleration. That leaves us with M1 plus M2 equals all the junk on the right side. M1G minus M2G sine of theta. And then we have to divide both sides by M1 plus M2. We do that in different colors since it's a different step. Divide both sides by M1 plus M2. We can't cancel anything out on the right side, so we're just going to write this out as we see it. And that'll be our last step for the acceleration. Again, hopefully you're writing smaller and you have more space than I do. So we'll put it over here. The acceleration equals, let's just plug and chug. M1, 5 kilograms, times 9.81 meters per second squared, minus M2, 10 kilograms, that's a kg, times 9.81 meters per second squared, times the sine of 40 degrees, all over 5 plus 10 gives us 15 kilograms. We get an acceleration of 4.4 meters per second squared. Now we have to do the entire problem over to find the tension force. But really, since we know the acceleration, let's look at the easier of the two equations. That's the first one. We just isolate f of t and then solve for it. So I'm just going to do it all at once. We'll add f of t to the left side, subtract ma. That leaves us with f of t equals m1g minus m1a. We'll plug and chug 5 kilograms times 9.81 meters per second squared minus 5 kilograms times the acceleration of the mass, 4.4 meters per second squared. We get for the tension force to be 53.7 newtons. And that's a tension force of 1 on 2. And that's it. One more problem to go. I can scroll. Okay. A 60 kilogram Chris snowboards down a 37-degree mountain. The coefficient of friction between Chris's skis and the snow is 0.72. Calculate the acceleration of Ian. Assuming that Ian starts from rest, what is his final velocity after 15 seconds? Assuming Ian is Chris. Let's do the calculations. Sorry, Chris. Let's make Chris be a dot, and we'll label all the forces acting on Chris. We can always start off with f of g going straight down, the force due to gravity, and we know that friction is counteracting Chris's force, so F sub F is going against him. And we also know that, I'll draw an inclined plane just so we can get an idea of what's happening. We also know that the normal force is perpendicular to the surface, so F of n is perpendicular to the surface. Just like the previous problem, we have to take our coordinate plane and rotate it. We're going to rotate it so our y-axis is perpendicular to the surface, and our x-axis is parallel to the surface. When we do that, we're now breaking up gravity into its components, Fg in the y direction and Fg in the x direction. Fg in the y will be perpendicular but going down. Fgx will be parallel and going to the right. And just like the previous problem, the angle between the ground and the hill is the same angle between Fgy and Fg. And our goal is to find, first, Chris's acceleration. Just like the previous problems, we're going to start in the y direction, because we want to find its acceleration in the x direction, so I'll save that for the end. So let's see here. Newton's second law. A equals F net over the mass. Same thing, multiply both sides by the mass. Ma equals F net. Now we want to break down F net. So we have two forces in the y direction. Fn is going positive. Fgy is in the negative y direction. Ma equals the normal force minus Fgy. In this case, Chris / Ian is not accelerating in the vertical direction. They're going down the mountain, which is in the horizontal direction. Ma goes away. The force of gravity in the y direction, since we know Chris's mass, we can calculate the force of gravity. The angle is 37 degrees, so we can calculate Fgy in terms of F of g. Notice Fgy is adjacent to the angle, so that'll leave us with, let's add Fgy to the other side, I guess. So that gives us Fn equals, Fgy turns into F sub g times cosine of theta. Again, that's because the vertical component is adjacent to theta. We can break down F sub g into m times g. which leaves us with the normal force is equal to mg cosine theta. Let's stop there and go in the x direction, because we can't break it down any further other than just plugging in our values. In the x direction, Newton's second law, A equals F net over m. This time we want to solve for the acceleration, so I'll keep it on the left side. In the x direction, we have two forces. Fgx is positive, f of f is negative. Fgx minus the force of friction all over the mass. We could solve for Fgx in terms of f of g. Notice Fgx is opposite the angle, so we have to use sine of theta, because it's Fg sine of theta, minus, we're given the coefficient of friction, but not the force of friction. Let's break down Ff into its formula, mu Fn, all over the mass. We know what we can calculate f sub g, we know theta, we know mu, we know m, but we don't know Fn. However, we solve for it on the left side, so we can plug in mg cosine theta for Fn. That gives us f sub g turns into mg times the sine of theta minus mu times f of n, which is mg cosine theta, all over the mass. Every variable has a mass in it. In this case, we could cross off the mass, and now we just plug in chug. The acceleration is 9.81 meters per second squared times the sine of 37 degrees. 37 degrees minus mu 0.72 times the mass again, times g, 9.81 meters per second squared, times the cosine of 37 degrees. Plug in chug and we get an acceleration of Chris/Ian to be 0.26 meters per second squared. And that's letter A. What is Ian/Chris's acceleration? Letter B asks, assuming that Chris starts from rest. So let's look at letter B. VI of Chris is 0 meters per second. He travels for 15 seconds. And we want to calculate the final velocity of Chris. We know VI, T, and A, and we want to solve for VF. We can use VF equals VI plus AT. VI 0, VF is going to be equal to 0.26 meters per second squared times 15 seconds, giving Chris a final velocity of 3.9 meters per second. And that's it for this video. I hope you're able to follow along, and I'll see you next time. Thanks for watching. See ya.